The other day, I didn't do such a good job um, explaining area between curves and area under a curve, so I thought I would start there today. Let's see. Can everyone see what's on the screen on your end? And you can type in the chat box if you want to answer that way. That's perfectly fine. I just want to make sure everybody can see what's on the screen.
Yes, sir.
Okay, thank you. And as always, and y'all know this from some of you who've taken Cal 1 from me, as always, if you have any questions, even after class, many of you email me through Blackboard, that's fine. Blackboard messages, and also many of you use that Ask My Instructor feature, help feature in my math lab. So continue to use those items uh, to reach out to me, and I'll be glad to help you as best I can. Today, I wanted to, like I said, I did not do, in my opinion, a good job of explaining area under a curve and area between curves the other day. So I wanted to go back over that briefly. Starting with, and I borrowed these notes from online, as you can see up in the toolbar, address bar, whatever it's called. Area under a curve that is bounded by the x-axis. If you're given a function, namely f of x, and it goes from a closed interval from a to b, and is bounded by the x-axis, then you can use what's called the fundamental theorem of calculus to find the exact area under the curve. So here is the area formula that's uh, an extension of the fundamental theorem of calculus, and we're going to use that to find the area. Let's look at this first example. And give me just a second. I'm going to screenshot this, put it on our paint board. And let me share the paint board. Okay, here we go. Find the area in the first quadrant bounded by the given function and the x-axis. If a graph is not given for you, then you don't have to draw your own. You can simply use Desmos, DESMOS.com to graph your function. Now, according to the graph, our function starts at 0 and it ends at 4. So that's our limits of integration going from 0 to 4. And our f of x is 4x minus x squared. For this problem, we can take the power rule for derivatives and undo it. So instead of subtracting 1 from the original exponents, we add 1 to each exponent. So for 4x to the first power, that would be 4x squared. And instead of multiplication, you're actually dividing by your new exponent. So we'll divide by 2. Oh, by the way, anytime there are questions in the homework or the quizzes that I know I'm not going over in class, I will usually either give you full credit for it, for those questions, or remove them and give you full credit. Now, this was simplified to 2x squared. And the integral of x squared, again, we're adding 1 to the original exponent. And we'll just divide by 2 plus 1. And that gives us x cubed all over 3. Now we're ready to find the area. And according again to your fundamental theorem of calculus, plug in your upper limit of integration first. So everywhere we see an x, we'll plug in 4 first. And this fundamental theorem, you have a mandatory minus sign in between your substitutions. And the second go around, everywhere you see an x, you'll plug in 0. So we got 0 and for each x. Now, everything in the second substitution goes to 0. So all we got to worry about calculating is the first substitution. 4 squared is 16. Times 2 gives us 32. 4 cubed is 64 over 3. In order to combine the number with the fraction, we need to make 32 a fraction also. So I'm just going to rewrite it as something over 3 so the denominators will match. 32, we can rewrite it as 96 over 3. And now we can easily subtract our fractions. So our final area under the curve is exactly 32 over 3. Out there in the World Wide Web, are there any questions or concerns about this first problem?
No, sir.
Okay. Did anybody else have any questions? Check in the chat box, and that's a no. Okay. So cut and dried, that's all you do when you have a function and it's bounded by, you want to find the area under a curve that's bounded by the x-axis. That's all you got to do. Well, what if you had two functions and they intersect and you got to find the area between the two curves? So let's find that. I'm sorry, I'm reading as I'm going. Let's see, let me look at the other notes and see if they have any better examples. Okay, if you have two functions or two curves and they are intersecting each other somehow, like you see in example 1, and you got to find the area between the two curves. What we got to do is use this particular theorem, definition, what have you. It says to find the area between two curves, and your curves are y equal to some x function. Then you do the integral from a to b of f of x minus g of x. In more informal terms, you're just taking the top curve minus the bottom curve. And this is why it's very important to go on Desmos and graph if a graph is not given for you, so you know which one is the top curve and which one's the bottom curve. So let me screenshot, copy, and paste this example, and we'll find the area. Find the area bounded by the graphs of y equal to 3 minus x and y equal to x squared minus 9. And again, if a figure is not given for you, go on Desmos and type these in to see which one is top curve, which one's bottom curve. Now, clearly the top curve is the line. Let me write down our formula. I'm so sorry. Forgot about that. Our limits of integration, the curves go from -4 to +3. And our top curve is the line 3 minus x. And the bottom curve is x squared minus 9. Now, before we integrate, we must take that negative sign in the middle and distribute it in the second parentheses. So that would be 3 minus x minus x squared plus 9. And we can actually add the numbers together. So that would be negative x squared minus x. And I just put it in descending order, that's all. Now we are ready to integrate. So the first term will integrate as negative x cubed over 3. Second term will be negative x squared over 2. And your last term will just be positive 12x. Next step, plug in your limits of integration to find the exact area. According to your fundamental theorem of calculus part 2, plug in your upper limit of integration first. So let's see here. Got negative 3 cubed over 3 minus 3 squared over 2 plus 12 times 3. Mandatory minus sign in between your substitutions. And second go around, everywhere we see an x, we'll plug in -4. And just make sure you got every single negative sign because there's a bunch of them. All right, now we're going to evaluate everything carefully. -3 cubed is -27. divided by 3 is negative 9. 3 squared is 9, so that would be negative 9 over 2. And 12 times 3 is 36. And we can go ahead and simplify that sum. Just put it up here. 36 minus 9 is 27. Minus 9 halves. Minus. Okay, now here, again, be very careful with your negative signs. A negative 4 cubed is negative 64. But you got a negative already outside the parentheses right here. So that would be a positive 64 thirds. Next fraction, negative 4 squared is 16. And negative 16 over 2 is negative 8. And then the last part, negative 48. And actually, I can go ahead and erase this part here because we can combine those together and get negative 56. Do anybody have questions or concerns so far?
No, sir.
Okay, thank y'all. Now let's distribute that negative sign times everything in the second brackets. So we have now 27 minus 9 halves minus 64 thirds plus 56. 27 plus 56 is 80, I think, 83. Now, in order to combine the number and the fractions, everything must have the same common denominator. So the common denominator is 6. And I'm just basically rewriting each part where it's something over 6. Here in the middle, 2 can go into 6 3 times. And 3 times negative 9 is negative 27. For the last fraction, 3 can go into 6 2 times. And negative 64 times 2 is negative 128. And to rewrite 83 as something over 6, just multiply 83 by 6. And that's 498. So I'm going to subtract the numerators. And our final exact area is 343 all over 6. Any questions about finding an area between two curves?
No, sir.
Okay. Now, this was a situation where you had top curve minus bottom curve. But what if you had, instead of y equal to some x, you had like x equal to some y term, and you had to find the area between the two curves. So let's take a look here if I can find one. And just a second, let me copy the problem and also copy the picture. All right, if your curves or functions are in terms of x equal to some function y or some term y, to find the area between the two curves, you're still using kind of the same area formula, but instead of top curve minus bottom curve, you are taking the rightmost curve minus the leftmost curve. So this is the slight variation of our area formula. Instead of top minus bottom curve, you do right curve minus left curve. And as you can tell, whenever your whenever your curves are given in terms of x equal to some y, to find the limits of integration, you just use the y values where they start and stop intersecting. So that's from -1 to 1. Our rightmost curve is 2 minus y squared, minus our leftmost curve is actually y squared. So I don't need the parentheses. Now we are ready to integrate. The integral of 2 is just 2y. And the integral of each negative y squared, oh, I'm sorry. We can combine those together, make it -2y squared. So the integral of that single term is just -2y cubed all over 3. Now we're ready to find the area by plugging in our limits of integration. So according to our fundamental theorem of calculus, part 2, I think, you plug in your upper limit of integration first. So everywhere we see a y, we plug in 1. There's a required minus sign in between your substitutions. And the second go around, in place of each y, plug in -1. By the way, the other day, because my lecture video had technical issues and I could not share it with you guys, I found some of my old YouTube lecture videos that I posted instead. So look in Blackboard announcements. I believe that's for lessons 6, 7, and 8, I believe. Now let's calculate. In the first brackets, we got 2 minus 2/3. Second brackets, we got -2. And right here, -1 cubed is -1 still. Times -2 gives us a positive 2/3. Now we need to distribute that negative sign times everything in the second pair of brackets. So I'm bringing down the first part without the brackets. And the second part, this will be a positive 2. And this will be -2/3. Now, when we combine everything together, we get 4 minus 4/3. To combine our whole number with our fraction, just rewrite or revise the whole number, make it a fraction. So we can make 4 as 12/3. Therefore, the area between the two curves, right minus left curve, is exactly 8/3. Any questions about finding the area between two curves?
No, sir.
Okay, thank y'all. Uh, the other thing that I didn't get around to covering at all is something called integration by substitution. Now, if you had a problem like this, integral of 3x squared dx, then you can easily find the antiderivative of that by undoing the power rule. This will be 3x cubed over 3. And it would just be x cubed plus some constant c. But what if you had something like this? Well, you can't use the power rule for antiderivatives there. We hadn't talked about any other integration techniques. So this is as good a time as any to introduce or reintroduce to you guys the substitution method. If finding the antiderivative by undoing the power rule is not available, then the next step is try substitution. And I'm going to use this second example to explain substitution. Typically, if you have a radical or if you have something raised to a power, then that's what you let u, as in ukulele, that's what you let your u equal to. So we'll let u equal to t squared minus 3. The dt means that eventually somewhere you took a derivative, maybe. So that's what we got to do here in our u substitution. Take the derivative of both sides. So the derivative of u is just du. And the derivative of t squared minus 3 is 2t. And the dt means that you took the derivative of t with respect to t. Derivative of t, I'm sorry, I got my tongue tangled there. Now, what we're trying to plug in is t dt, but we have a 2 in front of that t dt. All right, no worries here. You just divide both sides by 2. So t dt that we're about to substitute is equal to 1/2 du. We're ready to plug in to our original problem now. In place of t dt, I'm sorry, we'll plug in du. And you guys know any constants go outside the integral sign. In place of t squared minus 3, we'll plug in u. Now, we know from algebra that the square root of u is the same thing as u to the 1/2 power. Now, before we integrate, are there any questions about the substitution method? Okay,
No, sir.
Okay, thank you both. Now we're ready to take the antiderivative. So undoing the power rule would just simply add 1 to our original exponent. And instead of multiplying, the opposite of multiplication is division. So we'll divide our antiderivative by our new exponent. Now 1/2 plus 1 is 3/2. So we have u to the 3/2 over 3/2. And we know from algebra, when we divide by a fraction, we flip that fraction. And in this case, make it 2/3. So we'll just bring all that over here. And remember, if you're not plugging in stuff like your limits of integration, then you have to put a plus c when you're taking the integral of indefinite integrals. With the fractions, the 2's cancel out. And we need our answer because our original problem was in terms of x. We need our answer in terms of x. So whatever u originally was, you just back substitute that in. So our final integral is 1/3 times t squared minus 3 to the 3/2 power plus c. Again, are there any questions about this particular problem? All right, let's look at another example. This one involves trig functions. We have the integral of sine to the 10th power x times cosine x dx. With this basic type of integral, if just one of your trig functions is being raised to a power, that's what you let u equal to. So we'll let u equal to sine of x. Take the derivative of both sides. So du is equal to cosine x dx. And we can plug that in immediately. So what I just underlined in purple, that is our du. The sine of x is actually our u, and it's being raised to the 10th power. Now we can easily find the antiderivative by undoing the power rule. So this will become now u to the 11th power over 11 plus c. The last step, we need our answer in terms of x, so we back substitute u. So u was sine x, so that would be sine to the 11th power x all over 11 plus c. Are there any questions about this problem? Okay, in the chat box, thank you. Anybody else have questions? Let's look at one more example in which you have to use substitution. Let me see if I can find a fraction. All right, let's do number 8 here. All right, we cannot integrate it the regular way by undoing the power rule. So the only other method we've discussed is substitution. So let's figure out what we need to substitute. Since the top part is being squared, let's try making that equal to u. So we'll let u equal to, and I'm changing the square root of x to x to the 1/2 power. And let's take the derivative of both sides. So we have du equal to 1/2, and I'm just using the power rule here by subtracting 1 from the original exponent. So that makes it negative 1/2. And the derivative of negative 1, with it being a constant, is 0. All right, so we have 1 over, I'm just changing this back to a radical for now, 2 times square root of x dx. And hey, that looks almost like what we can substitute immediately. There's understood to be a 1 here over square root of x. And we almost have that. We need to multiply both sides by 2 to get that 1 over square root of x by itself. So we now have 2 du equal to 1 over square root of x dx. Now we can plug 2 du in place of 1 over square root of x. All right, so I pull the 2 out. The 1 over square root of x dx is our du. And square root of x minus 1 was our original u. And it's being squared. In most cases, when you use the substitution method, you end up with something pretty easy to integrate. So when we integrate, we have 1/3 u cubed plus c. And I can go ahead and multiply that 2 times 1/3. And another thing we can do is, since our answer has to be in terms of x, back substitute what x was, u was, I'm so sorry. So u was originally square root of x minus 1 cubed. And don't forget your plus c. Are there any questions about this problem or substitution in general? Okay, that takes care of lesson 8. Again, I have an extra video and Blackboard announcements for lessons 6 through 8. But what I will do either later on today or first thing tomorrow is if there are no technical issues, I will put today's video also in Blackboard announcements. If there are no questions, I'll see y'all next time, and y'all take care.
Okay, thank you, sir.
Thank you.